Every model in this series is wrong. Every Brownian motion from episode 1, every Black-Scholes formula from episode 2, every Heston surface from episode 15, every jump diffusion from episode 16. The statistician George Box said it best. All models are wrong, but some are useful. Wrong does not mean useless. It means incomplete. A model is a simplification that captures the essential structure of a problem. The question is not which model is correct. The question is which parameters make a wrong model useful. And that question has a name: calibration. Calibration is the bridge between mathematics and the market. Here's how it works. A model takes parameters and produces prices. That is the forward problem. You choose sigma, kappa, theta, feed them into the model, and out come option prices. Calibration runs that arrow backwards. You start with market prices, observed on a trading screen, and you ask, what parameters would make my model reproduce these prices? That is the inverse problem. This is episode 19, the grand finale of the math behind finance. We will learn how to calibrate the Heston model to an implied volatility surface. We will compare price space and IV space calibration. We will ask how many parameters are too many. We will test our calibration with 100 Delta-Hedge simulations, and we will see how neural networks are rewriting the rules. Let us begin. In the last section, we introduced calibration as a concept. Now let us write it as mathematics. Given a model with P parameters, we define a forward operator. FF takes our parameter vector theta and returns N model prices, one for each strike and maturity in our dataset. This is the forward problem. Parameters go in, prices come out. Calibration is the inverse. Given N market prices observed on a trading screen, find the parameter vector theta that minimizes the weighted square distance between model output and market observations. The weights Wi control how much each data point matters, and we will see later that this choice has profound consequences. But this problem is inherently difficult. The mathematician Jacques Hadamard defined 3 conditions for a well-posed problem. A solution must exist. That solution must be unique, and it must depend continuously on the input data. Calibration in finance violates the second and the third condition. Different parameter vectors can produce nearly identical prices, and small perturbations in the market quotes, even within the bid-ask spread, can cause the calibrated parameters to jump wildly. This is why calibration requires care. Now let me show you what calibration looks like. This is an implied volatility surface. Strike price on one axis, maturity on the other, implied volatility rising vertically. The red dots are 15 market quotes, and this blue surface is the Heston model with an initial guess for the 5 parameters. Watch as the Levenberg-Marquardt algorithm searches for the best fit. The surface bends, it twists, it pulls itself toward the data. After 12 iterations, convergence. 5 numbers now reproduce the entire implied volatility surface. That is calibration. The Heston model has 5 parameters. Each one controls a different feature of the implied volatility surface. V0 is the initial variance. It sets the ATM implied volatility for short maturities. Kappa is the mean reversion speed. It controls how quickly the term structure of volatility flattens. Theta is the long-run variance. It anchors the ATM level for long maturities. Xi is the vol of vol. It controls the curvature of the smile, how much the wings rise above the at-the-money level. And rho is the correlation between the stock price and its volatility. A negative RO creates the characteristic left skew that we see in equity markets. Now let us calibrate. We start with an initial guess. These values are deliberately wrong. The green ticks show where the true parameters are. The Levenberg-Marquardt algorithm computes the Jacobian, the sensitivity of each model price to each parameter, and uses it to choose a direction to step. Iteration 3. The sliders have already shifted toward the green ticks. The residual sum of squares has dropped by more than an order of magnitude. Iteration 6. Iteration 9. The parameters are now within 1% of their true values. Iteration 12. Convergence. The RSS has fallen below 10 to the minus 10. Every slider sits on its green tick. But here is the trap. Start from a different initial guess. This time, rho equals positive 0.3 instead of negative 0.3. The algorithm converges again. The dot stops moving. The RSS drops. But look at where it stopped. Rho is still positive, plus 0.31. The RSS bottomed out at 1.2 times 10 to the minus 3, 1,000 times worse than the true minimum. This is a local minimum. The loss landscape of financial model calibration is non-convex, riddled with false valleys. This is why practitioners never trust a single calibration run. They use multiple starting points, random restarts, and sometimes global optimization before fine-tuning with Levenberg-Marquardt. The mathematics guarantees convergence to a local minimum. It says nothing about finding the global one. There are two natural ways to measure the distance between a model and the market. The first works in price space. You minimize the sum of squared differences between model prices and market prices. The second works in implied volatility space. You minimize the sum of squared differences between model IVs and market IVs. Same model, same data. Do they give the same answer? They do not. Here are the implied volatility smiles after calibration at maturity t equals 0.25. On the left, IV space calibration. The green curve passes through every red market dot. Wing error, just 0.4 volatility points. On the right, price space calibration with uniform weights. The fit looks fine at the money, but at the wings, the deep out of the money put at moneyness, 0.8 misses by 3.7 implied volatility points. The model cannot see the wings. Why does this happen? The answer is vega. Vega is the sensitivity of an option price to volatility. It peaks at the money and decays exponentially toward the wings. At a deep out-of-the-money strike of K equals 120 with T equals 0.25, the vega is 470 times smaller than at the money. Squared, that is a factor of 220,000 to 1 in implicit weighting. In price space with uniform weights, the OTM option is effectively invisible. The remedy is simple. Weight each price residual by 1 over vega squared. This recovers the IV space behavior while keeping the smoothness of the price space objective. The lesson: the choice of objective function determines what the model sees and what it ignores. We have built 3 models in this series: Black-Scholes with just 2 parameters, a single volatility and an interest rate; Heston with 5, adding stochastic volatility, mean reversion, and correlation; and Bates with 8, adding Merton-style jumps on top of Heston. Each model fits the data better than the last. That is guaranteed. More parameters can only improve the in-sample fit. But is a better fit the same as a better model? 2 criteria answer this question with mathematics. The AIC information criterion, AIC, penalizes each parameter with a cost of 2. The Bayesian information criterion, BIC, penalizes each parameter with a cost of log n, where n is the number of data points. For our 60 IV quotes, log 60 is 4.09. BIC penalizes complexity roughly twice as hard as AIC. Here are the results. The taller the bar, the better the score. Black-Scholes is far behind. Heston and Bates are close. Under AIC, Heston and Bates are tied at -552. The 3 extra jump parameters earn just enough improvement to break even. But under BIC, Heston wins clearly. -541 versus -535 for Bates. The BIC penalty for Bates is 32.7, compared to 20.5 for Heston. Those 12 extra penalty points outweigh the modest fit improvement. The verdict: the 3 extra Bates jump parameters are not justified by the data. This is a moment to pause and see the connection. In machine learning, fitting a massive neural network to a small dataset is the same mistake. More parameters than data points, perfect training loss, and 0 predictive power. The shared mathematics is KL divergence, the foundation of both AIC and cross-validation. The remedy is the same in both worlds. Hold out data that the model has never seen, 80% for training, 20% for validation. A good model fits the unseen data. A bad model memorizes and then fails. In finance and in machine learning, the test of a model is generalization. If our calibration is right, the math says the hedge P&L should average to 0. Here is the formula. From Ito's lemma in episode 9 and the Black-Scholes PDE in episode 10, we derive the instantaneous P&L of a delta-hedged option position. It equals 1/2 times gamma times S squared times the difference between realized variance and implied variance. If the implied volatility matches the realized volatility, the P&L is exactly 0. If they differ, there is a systematic drift. Let us run 100 simulations and see. 100 GBM paths, each one rehedged daily for 63 trading days. The hedging volatility equals the true volatility, 0.20. The terminal P&L distribution is tightly centered near 0. Look at the mean, almost exactly 0. This is what correct calibration looks like in practice. The residual variance comes from discrete rehedging, not from the model. Now watch what happens when the calibration is wrong. Same 100 paths, same stock dynamics, but now the hedging volatility is 0.25 instead of 0.20, a 5 volatility point error. The entire distribution has shifted to the right. The mean PNL is greater than 1. That is a systematic gain because sigma implied squared exceeds sigma real squared. But this gain is illusory. It means the model sold options too expensively. In a competitive market, no one buys your overpriced options. The lesson? Calibration quality is not measured by residual fit. It is measured by hedge performance. A well-calibrated model produces a PNL distribution centered at 0. Anything else is a warning sign. Everything we have done in this episode, calibration, optimization, the forward and inverse problem, all of it rests on one assumption, that we know the right functional form for the drift and diffusion. Heston says kappa times theta minus v. Merton says add a Poisson jump. What if we let a neural network learn the drift and diffusion directly from data? That is the neural SDE. The equation looks the same. dx equals mu dt plus sigma dw. But now mu and sigma are not formulas. They are neural networks with thousands of learned parameters. Here is the architecture. The input is time and the current state. It passes through a multi-layer perceptron that outputs the drift mu phi and the diffusion sigma phi. These feed into an Euler-Maruyama integrator that simulates paths step by step. A separate network, the discriminator, compares the generated paths against real market data using the Wasserstein distance. And here is the key innovation. The gradient flows backwards through the entire SDE solver using the adjoint sensitivity method. This makes end-to-end training possible in constant memory. Let us step back and see the full picture. Every concept in this episode has a twin in machine learning. Calibration is hyperparameter tuning. Levenberg-Marquardt is atom. The non-convex loss landscape is the same in both worlds. And the neural SDE is the bridge where Ito calculus meets automatic differentiation. The mathematics is the same. The implementation has evolved. We started with a random walk. Episode 1, Brownian motion. And step by step, we built a bridge from pure mathematics to the trading floor. Along the way, every concept in finance found a twin in machine learning. Stochastic calculus became diffusion models. Optimization became gradient descent. The inverse problem became hyperparameter tuning. And the neural SDE married Ito calculus with automatic differentiation. These are not analogies. They are the same mathematics, applied in different worlds. 19 episodes. One idea, the mathematics that turns uncertainty into something you can write down, compute, and trade. Thank you for watching.